Well, Emily Dryden is the last speaker today. She'll talk about eigenvalue bounds for mixed Steklov problems in 2 dimensions.
Okay, thank you for the invitation. Thank you for your patience. I'm not sure why my computer couldn't see my iPad screen, but here we go. So the plan was to do a mixture screen and iPad talk. Maybe I'll use my board. We'll see how it goes. So what I'm going to talk about are eigenvalue bounds for the mixed Steklov problem, and I'm working just in 2 dimensions. So we heard a little bit about the Steklov problem yesterday in Yosef's talk, the first talk of the morning. What I'm going to talk about is a slight variation of that, but what he discussed was a special case. Okay, so I'll talk about the more general weighted Steklov problem. So what's my setting? My setting is that I have some bounded domain, let's call it omega. It's in a complete Riemannian surface, Mg. I want to think of the boundary of omega as being Lipschitz. And I'm going to take some L infinity function on the boundary. That function is going to be non-negative and it can't be identically 0. All right, so with that, we can define the weighted Steklov problem on omega. And as Yosef pointed out yesterday, we see that here the spectral parameter is in the boundary data. Okay, and the change from what he presented yesterday is that we have this rho. So we have the Laplacian of f is 0 in the domain omega, and then the normal derivative is this sigma rho f on the boundary. So if you take rho to be 1, we're exactly in the setting that Yosef was talking about yesterday. That gives us a discrete spectrum. Here there are different enumerations of the Steklov eigenvalues in the literature, so it's a little important to fix which one I'm using. I'm taking sigma naught to be 0 and then sigma 1 on up. It's a discrete sequence going to infinity. Okay, so it is important to note that my sigma 0 is 0. Sometimes people start with sigma 1. That comes into play when you're trying to compare bounds on sigma k or k plus 1 across different people.
So
all right. So
how does rho enter into this equation?
So rho is in the sigma rho f. So rho you can think of.
This is a product of sigma and rho.
Yes, yes, this is a product. So how should we think about this? Well, that's the next. How should we think about this? We should think about this rho as a density along the boundary. So these eigenvalues, these sigma k's, think of your domain omega as a freely vibrating thing. It's a freely vibrating surface, piece of a surface. And the sigma k's are the squares of the natural frequencies of that freely vibrating surface. And so that density rho is just living on the boundary. So motivation applications, Yosef mentioned a few. Katya also was talking about the Calderon problem yesterday. We have sloshing as another application. Recently, these have come up in work, for example, of Fraser and Shane about free boundary minimal surfaces. Okay, so the Steklov eigenvalues have been appearing in various places.
But you can have rho vanishing right on a part.
Yes, you can't have rho identically 0, but you can have rho vanishing on a part of the boundary. And I'll talk about that in a little while, that specific case. Okay, so I promised you that we would talk about upper bounds. So the story of eigenvalue upper bounds in the Steklov setting goes back as far as 1954 with Weinstock, who said, let's take some omega in R2, it's simply connected. Then we can find an upper bound on sigma 1 normalized by the weighted length of the boundary. And that product, what I'll refer to as our normalized Steklov eigenvalue, is just normalized by the length. That product is less than or equal to 2 pi. Okay, so it's a nice clean upper bound. We have equality if and only if omega is the Euclidean disk and rho is identically equal to 1. Okay, so here's a nice upper bound. It was later generalized. So it was generalized by Hirsch, Payne, and Schiffer in 1975. We have the same hypotheses on omega, simply connected domain in R2. And now we get a bound on the kth normalized Steklov eigenvalue. Okay, so we have this sigma k. It's on our domain omega with some weight rho, normalized by the length of the boundary, less than or equal to 2 pi k. So again, very clean upper bounds. They're just depending on where you are in your spectrum, right? Girard and Polterovich in 2010 showed that this is sharp. So here's my blank page to give you the example. Lacking the ability to write on that blank page, we will take Lior's suggestion and see if I can show you my blackboard. Can you see my blackboard? Great, thank you. So the idea is to take a bunch of sort of disks that overlap, okay, where they have this overlap of 2 epsilon. And what we're going to do is we're going to take a whole bunch of those. So we're actually going to take k copies. Okay, so we're going to take k copies of those disks. And what we're going to do is we're going to let that overlap tend to 0 so that we end up with k disks that just touch at a point. And that example is what shows that the bound is in fact sharp. Okay, so that example shows that the bound given by Hirsch, Payne, and Schiffer of 2 pi k is in fact sharp. And here I should mention they take rho to be identically 1 for those examples. Okay, so we have nice sharp bounds. Come back to that example, so maybe it's actually useful that it's on my board. Much recent work in this setting of finding eigenvalue bounds is depending on k, as we just saw with Hirsch, Payne, Schiffer. It's depending on the number of boundary components, and it's depending on the topology of the surface. With all of these bounds, the assumptions on rho and on the boundary vary. So just as some examples, there's recent work by Fraser and Shane, Karpukin, Yang and Yu, Girard, Polterovich, a lot of work around finding these upper bounds. But what you'll notice is sometimes rho is a non-negative function. Sometimes rho is a strictly positive function. Sometimes rho is constantly equal to 1, right? It varies a lot across the literature. But a nice thing is that there's a recent result of Bukur and Nahon, which we have then interpreted to say, actually, a lot of these bounds hold in a very general setting. And I think in the distraction of getting started, I forgot to mention my co-authors, so my apologies to them. This is joint work with, if I can I do it in alphabetical order? Let's see. Well, there are 6 of us. So this is joint work with Teresa Arias-Marco, Carolyn Gordon, Asma Hazanashad, Ali Ray, and Elizabeth Stanhope. This was another one of those women in geometry, the spectral geometry groups. So what we have done is we've said this work of Bukur and Nahon actually lets us interpret a lot of these results in the context of a general non-negative rho that's not identically 0, and in the context of any Lipschitz domains. Okay, so what their result, which was originally stated in R2, and we just observed that you can actually state it whenever omega is just a domain in a simply connected manifold, in a complete manifold. So given certain well-behaved sequences, you have a sequence of domains and you have a sequence of non-negative functions. Well-behaved here, there are some conditions it has to satisfy. If you want to know more about them, you can ask me, but I'm sweeping that under the rug. If we have some nice sequences, then we get that the limit of sigma k of those sequences is the sigma k of sort of what you think of as the limiting domain and the limiting weight rho. Okay. So the point here is that we're then able to say all those normalized Steklov eigenvalue bounds that depend only on topology are valid with rho arbitrary. So even if they were only originally proved for rho equal to 1, you don't need rho equal 1, right? Even if they were only originally proved for rho positive, you don't need rho positive. And so this allows us to go back to sort of that case that Dima was asking about. Well, can rho be 0 on some places? And so what we do is we re-envision that. That gives you sort of a Steklov-Neumann problem, which is what I'm going to talk about in a minute. So some of these bounds can actually be re-envisioned in this way. And in some cases, we can get sharper bounds by thinking about rho being arbitrary in cases where before it didn't have that flexibility. Okay. So for example, as just one example, Karpukhin in 2017 gave this bound on your normalized kth Steklov eigenvalue. Here, gamma is the genus and B is the number of boundary components. This was originally stated for the unweighted Steklov problem, so just rho constantly equal to 1, on domains with smooth boundary. And so our observation says now this holds for any rho on domains with Lipschitz boundary. Okay, so I've mentioned, and my title promised mixed Steklov problems, so let's get a definition of those, and then I'll give some more sort of interpretations of those kinds of bounds. So, mixed Steklov problems. Here we want to think of the boundary as being decomposed into two types of boundary. We want to have our Steklov boundary, and then we want to have the rest. And if we want to think about the rest having Neumann boundary conditions, as we have on the left, then notice what's happening. So we still have our condition Laplacian of f is 0 on omega, and then we have the normal derivative on the Steklov portion is just sigma f, so rho is 1. And then we have the normal derivative is 0 on this other portion, on the Neumann portion of the boundary. So this is a special case of the case I've been discussing. Okay, it's a special case where we just take rho to be 1 on the Steklov portion and rho to be 0 on the rest. And then, so Steklov-Neumann is a special case of this general weighted Steklov problem. A not special case, but related problem is Steklov-Dirichlet. There we're taking, again, rho to be 1 on the Steklov portion of the boundary, and the function to be identically 0 on the rest of the boundary. In both cases, you get this, discrete sequence of eigenvalues, as people are used to, and there are specific examples where each of these is interesting. For the purposes of time, I won't go into that too much. In case you don't think about this regularly, how should you think about it? Well, you should think about some heat distribution. And through the Steklov portion of the boundary, the heat flux is proportional to the temperature. And then on the Neumann portion of the boundary, we're perfectly insulated. Or on the Dirichlet portion of the boundary, we're held at temperature 0. Okay, so we're modeling this heat distribution. All right, so as I said, Steklov-Neumann is really a special case of that general weighted problem. So what that means is that we can really think of these bounds that we were getting in the general weighted problem as immediate bounds on normalized Steklov-Neumann eigenvalues as well. Okay, so why is that? If we start with a general rho, there's going to be some new metric conformal to our metric g that we started with, so that now we can think of it as a Steklov-Neumann eigenvalue with this new metric g tilde. Okay, so all those bounds we had in the weighted Steklov case are now bounds on normalized Steklov-Neumann as well. So let's go back to that Hirsch-Payne-Schiffer bound, which was 2 pi k, right, for the kth normalized Steklov eigenvalue. Let's set rho equal to 1. That's merely for convenience. So here's a theorem. We've said, okay, let's take a simply connected domain. Let's decompose our boundary into these two pieces, these two disjoint arcs. Then we can say something about the minimum of the normalized kth Neumann and normalized kth Dirichlet eigenvalue. It has to be less than or equal to 2k minus 1 pi. Okay, remember that Hirsch-Payne-Schiffer gave us that the kth Steklov was less than or equal to 2k pi. So we've managed to knock it down by pi. Okay. So we can apply this to improve known bounds, but first I want to give you an example. And the example is really just to show you that board again, right? If we now think of putting boards are better than iPads, right? So if we now think of putting a little bit of Neumann boundary on there, and then we let that collapse down, well, then we know that our kth eigenvalue here was 2 pi k. Right? We know that that was the case. So what does that tell us? That tells us that our min of our two eigenvalues has to be the Dirichlet one. Okay, so we actually get control that the Dirichlet one is the minimum because the Neumann one was 2. Okay, so the minimum is smaller and it was 2 pi k. Okay, so I mentioned how Steklov-Neumann is really the same as what we can think of as a sloshing problem. And in sloshing, we have this weak John's condition that lets us say something about certain types of domains. So where I first saw this was in a paper by Benuelos, Kolzitsky, Polterovich, and Siudeha from 2010. Sorry for butchering some names, I'm sure. Where they showed that in dimension 2, the kth Steklov-Neumann is less than or equal to the kth Steklov-Dirichlet. So what does this weak John's condition mean? Well, there's a picture. Ignore that for a second, but just look at the picture, which I was going to insert. And the picture says we have some nice boundary on one piece, and then the rest of the boundary stays sort of within certain a bounded region. So if we have a domain that looks like that, then we get that the minimum of those two eigenvalues, we can apply our theorem to say that the minimum of those two eigenvalues is the kth normalized Steklov-Neumann, which is less than or equal to 2k minus 1 pi. Okay, so here we again get an immediate bound applied to this condition where our domains satisfy a weak John's condition. And in fact, that bound is sharp. So here's my picture for sharpness. So here I'm just looking at the first normalized Steklov-Neumann eigenvalue. I have this interval I across the top. And the domains that show that it is sharp is just take I, cross the open interval negative n to 0. So just rectangles. As n goes to infinity, the normalized Steklov eigenvalue goes to pi. Okay, you know this by an explicit computation of the eigenfunctions. It's a tanh, and it just goes, it's a hyperbolic tan, and it just goes right to pi. So that example shows us that in fact, this bound, which was less than or equal to 2k minus 1 pi, that bound is sharp. Okay, so to summarize, the idea was that we wanted to try using this observation that Bukur and Nahon's result gives us lots of immediate extensions of known eigenvalue bounds to cases where the weight can be more general and our domain is just Lipschitz. We wanted to apply that to different known eigenvalue bounds, see what improvements we could make. And then in some cases, that also leads to a Steklov-Neumann problem. And that got us thinking about Steklov-Neumann and Steklov-Dirichlet. And in there, we can also use some of these ideas to get improvements of existing bounds. So thanks for your attention and apologies again for the technical difficulties.
Really, thank you very much. for a great talk. Are there any questions?
So I have a quick question. So the paper by Bukur and Nahon, so their main goal was to prove instability for the Weinstock inequality. However, if you look in one of their results that are not, I think, positioned as the main result, there is actually a stability statement, and stability in the sense of certain distance and certain Sobolev space between measures. So I'm curious whether you should be able to get the same sort of a stability result in your case. So given that your inequality is sharp, you can say that if you are very close to the limit, then you should have something similar to the cylinder or a statement of that kind.
Right. Yeah, we haven't looked at that, but that's true.
That sounds very plausible.
It does.
Yeah.
Thank you. Right. The focus of theirs is instability, but I will look at that. Thank you.
Yeah. Okay. Thanks for the great talk.
Does anyone else have any questions? Would anyone like to ask? Well, if not, let's thank Emily again, and also all the speakers for today.
That was a great talk.